welcome everybody. It's a real pleasure to welcome you to participate in this two seminars, international seminars that are going to be delivered by our friends from China, Professor Yuki Ma, okay, and Professor Wong. Well, the first seminar is going to be delivered by Professor Yuki Ma. He is a professor at the College of Optical Science and Engineering at Zhejiang University and director of the International Research Center for Advanced Photonics at Zhejiang University. He received his bachelor's degree from Lanzhou in China University in 2000, and his PhD in science from Lanzhou University in 2005. And from 2005 to 2010, he conducted scientific research at the National University of Singapore to succeedingly as a research fellow and research scientist. In 2011, he returned to China and joined the College of Optical Science and Engineering at Zhejiang University. Today, he has published over 150 papers in internationally renowned journals such as Nature Materials, Nature Communications, Science, Advanced and Physical Engineering, Technology, including awarded Conference Prize of the Provincial National Science Awards. He was elected into the New Century Excellent Talents in University programs, sponsored by the Ministry of Education in 2011. The Zhejiang Provincial 2000 Talents Program in 2020. Currently, he serves as an associate editor of the SCI Journal Materials and an editorial board member of Florence Electromagnetic Letters, and as editor of the IEEE Journal of Selected Topics in Quantum Electronics. Please welcome Professor Ma to the board of
Thank you very much. And it's a great honor for me to be here and all of my colleagues. And I have, close collaboration with the team of Professor Hugh, and we knew each other from 2019, right?
Yeah.
And we visited this 2 times, and very good friends. And also our team and our research center with you also have a national project, so closely, both physically and electronically together. Okay, and today we will present a talk on the matter surface and talk about PPP, that the matter-based compact operating system, which is a real content, a kind of spread. My name is Li Ma, okay, from Zhejiang University, College of Optical Science and Engineering, and we have specific department, and the keywords is photonics or optics, okay, in China. First, I would like to give a simple introduction about the city where we are. We are Hangzhou City. This is in China. This is Beijing. This is Shanghai. This is Hangzhou City. This is South Korea, Japan, and this is India in here. This is Singapore, Malaysia is here. So basically, we are east side of China. This is some data about Hangzhou. Hangzhou is the capital city of Zhejiang province, east of China, and we have more than 1,000 years history. Used to be the capital city in the history of 200 years in Chinese history, and it's just a tourist city and also full of high technologies. And the GDP of last year is about nearly $300 billion. Okay, the population is also huge. We have 12 million population. Yeah, maybe for the young generation, you will say, right? You say is set up by the alumni of Australia University, and this is global. You know the unit tree. You have not been keep talking. You notice that also, yeah, from our alumni. This is green, a black eagle, and what you can make screen. Yeah, also from Europe. Of course, we have the three countries that Alibaba, Alipay, something also, yeah, yeah. This is the company. Yeah, that's some time to give some minutes to introduce our university and our college. From Australia University, and according to the certain rank, we are the third one, yeah, number 3 in China. And the Beijing and Tsinghua University, like the Oxford and Cambridge in the UK, the third one we thought that's all. And last year, I think it's rank that one in 13, yeah, 33. Okay, we have 7 campus and 13 high schools and 7 affiliated hospitals. Okay, we have yeah, international students 2,000. Yeah, around the yeah. The image about our culture of the science engineering, and domestically, yeah, in the last 15 or 20 years, we are always ranked #1 in China according to the discipline of optical engineering. We call it optical engineering. The Zhejiang University and photonics, optics, not photonics, because it also has some research into the physics and material science combined together. And that was ranked by US News. Yeah, Zhejiang University Optics, so the group was the #1. The second one is Stanford University. The third one is the University of Singapore. Okay. Now is that we have huge manpower work on the field of photonics. Okay. Yeah, we have very many research institutes. Okay, research institute at national lab, conventional lab. Okay. This is roughly some figures, research lab. In the last 5 years, each year, 200 million, 200 million are getting into the 100 million. I'm sending research grant our members.
What dollars? The dollars.
Chinese, yeah. US dollar divided by 7. So, yeah. This is a scientific papers. Usually, yeah, the papers 200. Our faculty member is around 90. Professor, associate professor, assistant professor together. The number is 90. Yeah, this is the direction. Our college of the material device and of the nature system of the sensing and the emerging photonics. Very broad, almost cover each direction that can be researched, that can be conducted in the university. Okay, this is some papers, yeah, from our college. Every year, our college, 2 or 3 science or nature papers published. Yeah, Zhejiang University this year to this moment, we already published the 30 nature science or cell papers as the first organizations. Okay, we have students, our colleges, totally around 1,000. Among them, this is the undergraduate, this is graduate, this is a PhD. Yeah, we have a big portion PhD, they are researching type of university. And yeah, this is a PhD above. We have 4 PhD there. Okay, that's basically image about Hangzhou, our university, and our college. This is the outline of my talk. I actually work on because work on material, not metal surface. Metals about 2 kind of applications. One is for the metal device or related to talk. The other one is actually to for the near field transfer or thermal radiation. Today I will mainly focus on the first part of the metal device. I have two subjects. First, in very simple introduction, I assume that most of you are already and know about the material. A material that compared to the natural materials, which is more natural agents. The material is kind of memory artificial structures in 2D. Initially, 3D. When it was proposed by Professor John Henry, okay. Because interesting that we can not only cover the second and the fourth quarters, but more importantly is that third one might be the negative connectivity and the negative connectivity. This have effect index is then we get to something that the material cannot allow us to realize. We can break the physics of the units from the neutral material. Okay. And now people are more focused on the metal surface that since 2011 and Professor and later also from Harvard University and proposed similar structures that can generalize the interface Snail's law, and the new one 6 months later, another science paper published by Schlepp. Yeah, because Schlepp can almost that Schlepp reviewed the paper submitted by also the quality students. Now this conception has hugely extended not only the reflection or reflection, but any 2-dimensional structures or field-based structures belong to the scope of metal surface or generalized dimensional distribution. And work on intensity, work on the direction, control, and also angular momentum, or spectrum, or polarization, or the omnidirectional information, or spin off many factors together don't be controlled by the artificial structure. So there's duality. Okay. Now, once that you can make the device very compact, so high integration, no power consumption. Also, manufacturing because we can integrate this artificial photonics structure with 2-dimensional materials or with some materials to make optoelectric response. Many important things. Most important things are the promises that we can another one is the design on the optical lenses, and especially for calculating the technology utilized in the new generation of the mobile phone. We are already being done actually. How to commercialize things why I want PPT slide to introduce them into the or commercialize this kind of new material, new design. Okay, this is a basic flow. How to design metal surface or metal divided. Of course, you have idea what kind of thing you want, what kind of office you want, or factory you want, and then you just some basic software layouts, like a CST or a console, or we can have our own code, and then we will replicate and then testing and performance. can proceed to design this one. And for production, and usually in the lab, we use it as short technology plus the etching for visible light. And for the polypharida, we use direct laser lighting. Here I show that it's called mass production method. First one is the photography, and actually the companies now commercialize the product and mostly use this kind of technology because for metal surface the metal lens, the picture size 100 nanometers is not right. But for photonics, you have so many in China because the development of electronic components, and we have many EUV machines available in China. And EUV is many machines that can work on 28 nanometer for using for mask of the and structures. The second choice is manufacturing. Yeah, we have some analyze some spin-off companies that they work on this approach, especially for DOE. This is quite natural technologies. Okay, this is the fundamental instruction about the conception and function of industry or research slides. First of all, the research I want to design this application of a micro lens arrays enabled by metal surface. Okay. Micro lens arrays has been widely used already in our product. The first one is display, and each sector you have this one to connect this, or this is 3D cameras to have images. You might also to have the gas information. This is all the communications, and this is a bi-networks or energy connection. We are also using this micro lens. Of course, the LED, each LED has micro lens. Then why we use the metal surface to lens structure to replicate the lens. Because the lens, we can use the lens technique rule. There are many advantages because it is everything using the active structure, high application precision is much the performance is much better regarding the precise, especially we can fabricate freeform micro. That's very important. Okay, and we have the design flexibility, and also we have the manufacturability. So we can control not only the testing but also coordination for the tools. This one is very important. And for example, for the 3D perceptions, right? Currently, you have the using testing and to have the point out, and then you have camera and use the then can have to restore the gas information using the difference of view. And in this case, just in testing, once you add the polarization, in that case, some difficult scenario, for example, high reflecting scenario can be the challenge can be removed. This is why now people to more experience into the natural technologies. Yeah. And the last other way the broadband awareness specific population and direction and correction, and also compatible with mass production of semiconductor okay, I just list a few. One thing we are using this micro lens is the B-steering system. Because semi-solid B-steering quickly. You see that B-steering is one we use in China often I didn't say that in in Brazil, I haven't seen a car, leading car in your street. You have to be car, right? Yeah, but I haven't seen one. But in China, you see maybe at least 30% are EV cars. So amongst the EV cars, usually they will equip the LiDAR already. So this is yeah, they can drive the car by themselves. Currently, they use the mechanical one. Mechanical one is larger. Okay, it's complicated. The second choice is the flash. You have a pixel. The flash, you see that the chance is that just a short distance from radar, you need at least 100 meters away. So you can see in the dark at on far object. The third one is the OTA. The OTA, the issue that on chip can be very fast. But the question challenge that the energy is very weak, and the exercise it's hard to make a larger exercise, even big size unlimited. In other case, the resolution is also limited. One means that it has its own advantage. This one also has an advantage, but this one is slow, this one is fast, but this one can be very short distance, but this will be fun to see. Staying here. What we propose is that the idea is actually somehow simple forward. This is one layer of micro lens. This is online one, right? And just shift one of them to the displacement. And because the light comes here, parallel light falls here. And the plane of this one, in this case, the output line will be controlled to just the displacement one of them. Of course, we need to correct the aberrations in this case. So with that is done with another surface. Okay. This one, because we just using the piezoelectric to drive the oscillation of the motor. So they can be very fast, and because the size can duplicate the micro lens, so to make a larger beams. Okay, the energy can be high. This is some design, and yeah, you see that you can control the deflection of the beam just by the to shift the to create the displacement of the two lenses. Okay, the design is the quality is very good. And we manufacture in our lab. This is we have actually have three layers of a metal surface. Okay, one is double F. This is centimeter result. This is a measured result. I mean, the beams at the different angles. So the quality of the beam, more than 60, replicate the simulation once. Okay. Yeah, and this is the spot we measure at different diffraction angles. Okay, this is one spot you see that scan in the space. That average angles in the people altitude is around 20 miles. And we also do 3D scan with some artificial model here. And you see that's very quick because it's an oscillation. And there's a point you see that scan and regenerate depth information. This kind of thing with a very high speed and high angular resolution, also spatial resolutions. After completed this work, and we found that this when we displace these two layers, actually there are some diffraction orders, different diffraction orders. We found this kind of diffraction we can be utilized to measure the shift of the vector distance. Okay. The previous work, they utilized this shift, right, to control this theory. The second experiment, we use this kind of satellite to measure the lateral displacement. You see, the lateral displacement measurement is very important for many in the scenario manufacturing. Okay, to know that this, yeah, where the position is. Okay, we just utilize the diffraction effect. We have a different effect because of the water structure. We have different diffraction orders. We shift one of the layer and the intensity of each diffraction order can be changed, modulated. So I just measure the intensity, monitor the intensity of different diffraction orders, and then I know where the position of where the displacement of the value is. Okay. And some calculation and sensitivity regarding the position and the intensity change. While we use medicine, you can see from here our metalents. This is the field of this metalents. The F is the formula length of the metalents. For metal surface, we can make this ratio very large. Very large. Because metal surface just will be very small components. In our case, the sensitivity is much higher than the traditional one. And now we conduct the experiment, and I just showed you the result. Every I'll show you that we can measure different orders from 0 to 30. Yeah, to X and Y directly have different diffraction orders. Okay. That means that we can do two-dimensional position and scanning. Okay. We can measure in a larger range. This is the result. The experiment rate and the minimum displacement so we can recognize is 500 meters. Okay, that length is large, but just the 500 meter displacement and the signal can be recognized. Because we carry we did experiment in somehow this kind of environment, the sensitivity of this is actually a signal is very strong. Recognizing is very strong, you can see that. Yeah, you will put the percentage in the working environment, okay, or stable environment. The precision in detecting the current could be much smaller. This is a single technique and can be very large range. I mean that this one is not a relative measurement of displacement. This is the absolute measurement of displacement. So this one is very important. Means that larger range, high resolutions. Okay. You will have an address in just the formula at any time. Yeah, another work we show you here is using the metalents or lens to realize thermal large field camera. Large field camera that the large field camera. We have in COVID-19 and we have a thermal camera to measure the temperature at the airport and people's temperature. But in that case, you only have the temperature. To have the temperature, you need to know the distance the people to the camera, right? Then you can utilize some order equation to calculate the energy, to calculate the temperature. That means that you also need a visible light camera to there to measure the temperature. Also measure distance. Here we have a diagram. Can we use a thermal camera to get the thermal image? Meanwhile, also I can get the distance, like thermal distance. But that's a challenge. For this light, we have a large field camera with the light. It's vastly easier in the calculation. Because for visible light, I will have the truth here, right? Reflection. And you can see the features, right? My skin feature. You have the textures, have textures. But for the thermal image, you see this is the picture captured by the thermal infrared camera. You don't have the texture in the calculation. It's very challenging to get to reconstruct the distance. This is the way why previously people never tried this kind of thing or transplant the technology from visible light to thermal field. Okay. Yeah, we're doing the work and fabricate the metal lens array, micrometals array using the silicon or silicon substrate. Okay, we assemble the one and the chips provided by a local company. In China, we do things somehow easier because Hangzhou City and just inside the city, we have 2 or 3 producers that manufacture this kind of sensor chips. For this one, you have to closely collaborate with the company. You know why? Of course, we need to seal the metal surface inversion with the chip. Inversion. In the experiment, we cannot do. In our experimental environment, we can work. As country, we have specific facilities to do this. Okay, we take this kind of advantage. Okay, we fabricate a device, and that's why I need to answer that we can do this one, or we realize the thermal 3D camera. Because of the calculation, because of the big language model. Not a big language model, right? This is a challenging to imagine. Right? We need a higher computing power, performance, but because it can process very long words, and you can understand it better. Here, also, we utilize this kind of idea. I have many micro lens. Each lens captures a certain part of the scenario. And then each lens carries unique information. I just put all the unique information together, let the machine to learn, and then can understand correctly, more accurately, the infrared image. Although it is kind of a ghost image without textures. This is the free one. This is that. Also, it's combined with transformer created design. Then you can see this is the image, infrared image. Okay, this is each camera, each micro lens, to capture the image, that picture, using the classic technique that can be used for visible light. You can see that you cannot restore the rebuild this original image, but using our transformer-based technique of framework, you can precisely and reconstruct or rebuild the target. And this is the camera, and we have tested the accuracy of this. And for depth, okay, to the depth, this is ground truth. This is the values. You can see that the accuracy is very high using our technique. Okay, we have made that big because we trained this set up and we store the results, and then it has this is a car, small car, of course, it's a toy car with a temperature. This is one target, it's another target. This car is moving from here to here. And that's we can directly to give the output of depth. Okay, this is a different time scale. Actually, five pictures, they are only cost 0.5, 0.2 minutes. Okay, 1 minute give us 25 frames. So basically, this can be utilized for particular application. Yeah, we just use the one camera and thermal cameras. We can predict the position of the object. And we also use utilizing the metalentes to make thermal environment camera. Because we use some design, a traditional method, we have many lengths in order to have a high quality, right? In the high quality, you have the many to correct the aberrations. But this is heavy, this is bulky, this is expensive. Whether we can make it cheaper, okay, lighter, and we use two such lenses and geometry lenses using one lighter surface. Okay, this one lighter surface, we can have a similar quality. So this one many times that we are very excited to utilize this kind of design. This year and next year, we will see the product that in the market with that surface for thermal environment band. Because thermal environment band is a good answer. The face, the issue. What's the peak difference? Thermal photons. Do you have any idea? My face image thermal photons, right? Yes, spectrum. X-axis is spectrum, Y-axis is intensity. Where will we get the peak? Which wavelength?
So micros?
10, around the 10, right? Visible light will be 0.4, 0.5 microwave, 10 times smaller, or thermal luminance 10 times or 20 times larger. That means much more easier to fabricate. Right? This light is very challenging. We have one experiment to fabricate a visible light metal surface. This one cost us how much? 2,000, less than 10,000 VP. But the visible model cost us 27. The price is equal to the car of Tesla. Just one. Was 13 millimeter by 30 millimeter. I asked one local fab to manufacture. It's very expensive for visible light, but this one is very cheap. That's why industry are so excited. But visible light in China, this last month, you see, China we have the photonics show exhibition, right? Every year. Our work is solve some spin-off company utilizing the same design for photonics of visible light. Yeah. What's the advantage that once you produce this one in a massive, then the average price will be much lower. Because I just packaged one chip right in my lab. That was very impressive. But if you manufacture in many production, it's one chip. What's the gain they acquire using this kind one piece of metal surface. Because traditionally in the microscope, in microscope, right, you have many lengths. Usually it's 6, 7, 8 pieces of the length. This length, many of them are free-form lengths. You know free-form lengths, right? Free-form lengths expensive, not cheap. But once I'm using one metal surface, in that case, I can use spherical lens. Spherical lens. It's much cheaper. Yeah, reduce the price. So now, the things we can also utilize them in the visible light because we have the mobile phone, right? Mobile phone, so many globally instead. Okay, we measure the result and the categorize and also on the local handle, the using this camera, I just I use my lens with fabricate and and replace the product and measure you see that the quality almost good with the existing methodologies. Okay, until the light and the cost is much lower. Not much lower. The calculator is half cost to 37%, 50 to 7% cost compared with the traditional methodology. But this is enough for a company to replace the previous traditional design. Oh yeah, there's a matter of basic management and this is reflection. You have a lot of the university classification is a kind of lens. You can apply the position, and also the reflection is the logo of the university. The classification is a kind of reflection is a hologram, and the classification is hologram for 3%. This one in that case, you can do as actually something not. But this is the metalentes related or related to realize the imaging. Second part is also a metal surface, but what is related with the control of thermal photons. You see that. First one is what we want to show that the concept of black body cavities. Traditionally, we have black body cavities, two designs. The photons enter the cavity and reflect many ways, and they cannot find the entrance to get out and absorb them. That is huge. Now, we use the technology to measure scanning of microstructures can also trap light. Okay. And this is evolution technique, and I show you that this is the visible light image of this structure. The material is steel. Any metal actually we try the more than 10 metals. It doesn't matter. Similar result. And you measure the thermal pictures at the same temperature, and then I'll put on the same bakers, and you have different comparison image because of the absorption is different. And from this result, you can see this is depth of the hole, and this is the real temperature of this displayed temperature, or this is a calculated the intensity. You see, certain cases we can realize that the intensity for this whole measures or the microcavities can reach the unit. It's very high intensity, and we use this kind of method to turn the metal into a good absorber in a wide band. One way is to change the control the diameter of the hole in many holes. The other way is to change the depth. Okay. One way is This one is very dense. Almost nothing changing the values. Most methods are very efficient, control the frequencies. And this is the effectivity from 2 to 20 micron. This is the effectivity. That's not very small. This is 1,001. This is very small. This is our sample. The big one is the traditional. Yeah, our sample is very dark. Okay, this is using the integrated scale. We measure the utilities. Yeah, you see this good and from visible light to the non-infrared, very small. Okay, we want the things to some interesting temperature. The first one is the fixed laser thermal encryption. Visible light, you see this one, but yeah, visible light is actually this one. Naturally, but the thermal camera we have this one. Visible light is nothing, but thermal camera we have this. Called color. Okay, and this is the visible light. This one, but the thermal camera we have the lens weight. And this is also measured by the thermal camera. Visible light, this visible light is this, but once you measure the thermal camera, you can see that this is the true pictures. Yeah, you see, we can actually control the local intensity of the picture. Okay. The last piece, just that is to use using the net surface to control the polarization. Okay. This way, the thermal emission is without polarization. And we can design some structural metalentes. And the key design idea is that you need to bring the image. You want to have the left and the right hand characteristics. Okay, there's some technique on the design areas. You can see how the inputs are here. Okay, and this is the simulation result at a certain frequency to work dense. You just have very strong absorption of emission on left hand or right hand structure. Okay, and you can change the modulate the local structure so that can have different absorption properties. This structure absorption that hand that one is one hand, or this one may be 80%, that one is 20%. You can just modulate the fine structure. You can different absorption properties. Then you can control this one. This is the thermal imaging for this normal surface. But when you measure the left hand, taking this structure, you will measure the right hand photons, and for the same sample, and you will have this structure. Okay. But this is just a testing. Okay, now we can use the left hand, you have Einstein, the right hand, you can got Maxwell from the thermal imaging. This form, yeah, and we can do some other applications, the thermal digital imaging. Why we utilize this kind of correlation model other than test? Because for the Stokes matrix or imager, can see that the body intensity actually the contrast is very low. Right? But once you characterize the source parameter, for example, the S3, the contrast is much higher. Okay? And we can also remove some noise in the image. Because we didn't have this noise. This is the intensity of the polarization of the photons. This one can be removed from the accuracy higher. Okay. Okay, last PPT, I will some lecture notes, some instruction about the commercialization. I don't know whether in Pakistan, but we have the similar activity or not. And in China, very hot. And the current stage, how to utilize this kind of research. 10 years ago, a student asked me, Professor, what you are doing can be utilized in the industrial law. At that time, I said that, yeah, very promising. And in 5 years, we get utilized. But now, already utilized. This year, this is the iPhone, sorry, this is Chinese. This is the iPhone 17 model, right? Who have this model? Just announced this model. Yeah. But in this model, we already have this metalentes for the Face ID. Face ID, we can capture not only your photos, but also know their address. So it's not easy to misuse your mobile phone. Sometimes very more time in case you just use a picture and then the door will be open. But with this kind of cameras, it's not easy. Especially when we are looking at collaborating with the company. Not only 3D depth, but also spectrum. That means that people with temperature, right? You have very low animals, right? They have a temperature. You have a spectrum. Okay. You bring this not 3D imaging with spectrum. Hyper spectrum 3D imaging. Then it's not easy to choose the camera. This comes in now we are under the research. Okay. Yeah, this is a kind of many doctors to inform. And this is a MacBook here for last year. We have I think together at the end of each year, usually the group needs to get together to easy to drink. I can see again. Chinese will learn food. And the students, of course, we are choose basically professor will usually we are sport. I sport the air ticket. Air ticket. So they usually they will pick up from east to the west or from east to the north very far away. So I have advertisements for the air. Okay, currently we have postdoc positions are available 1 or 2 number of times. Medicine is related. Okay. 2 years, can be 3 years. Okay, even 4 years are okay, depends on the result. And the salary is compared along the skills. Yeah, competitive. In China, the tax rate is much lower than Western countries. And the expense even lower than Brazil. So, yeah. So the expense is very, relatively small compared to the other part of the world. So we want to attract talents to build up. And also have postdoc issues, want to even more is okay. Yeah. Yeah, that's really good more to okay. Thank you very much.
The session is open for questions. Professor Miguel Mates. Export. 3 short questions and the materials for the wavelengths is always silicon and silicon dioxide, and the other one is for the LiDAR imaging. You're using, I mean, it has to be like eye safe wavelengths, is it like 1.55 nanometers?
Yeah, okay. Regarding the material, it depends on the wavelengths, the spectrums. And for visible light, we're using the titanium oxide or silicon nitride. But in our experiment, we use silicon nitride because this material is much more negative industrial. But for the thermal imaging, thermal infrared lens, that one we use the silicon content.
Yeah, because silicon also absorbs below 1.
Yeah. The second, I mean, for the 8 to 12 micron for the thermal movements.
But sorry, so just another question about the micro black body. Actually, I didn't understand exactly. I understand what it is, but they're using it to somehow get in the image, like it was like a bolometer. It changes the temperature and reads. Is that how it works?
Yeah, get the image.
So the thermal image goes to those black body, heats up each one of them, and that's translated into temperature.
Yeah, you're right. Temperature, emissivity, then the formula, then you have the intensity of each part of the face skin.
Yeah, but since using as a detector, not an emitter, is that?
We have we have the array, right? We have sensing array. Because we have the camera, we have the lens. Behind the lens, we have an array of the sensor. We use actually this vanadium oxide, the root temperature sensor. We use the 500 by 500 arrays, I mean the sensor array. It's a chip. Somehow it's like a CMOS. Somehow like
that I understand. I'm saying there's an array of this micro black body.
Oh, micro black body, sorry. Okay.
Micro black body.
Not a micro size, actually it's a 100 micron.
That's fine. All I'm saying is, while you're using it, you don't use that for thermal imaging. That's my point.
Yeah.
How you're using that, I didn't understand exactly how you're using the micro black body array.
How to utilize this kind of thing?
What are you using it for?
Okay.
It's just a demonstration to get the temperatures and heat it up. We have different black bodies, and it's a demonstration. I didn't understand what you use it for.
Okay.
No, I thought it was a great idea, but I don't know what you were using it for. I mean, I didn't understand. I don't know. Perhaps somebody else understands.
Yeah. For example, this is encryption, and actually, yeah, this is visible light. Can get nothing, right?
I got it. Okay.
Yeah, for some images you have this one. Okay. Actually, this one, you see, we fabricate this one on metal, any metal. Tungsten, high temperature, high melting point can be utilized. That means that sometimes the military, they are very interested because usually the black body is molecule of something, right? Paste, glue something. It can be not utilized at very high temperature. High temperature will destroy the material. For our case, then we can elevate the temperature to 800 Kelvin or even higher because it is made of metal. So, and we also actually can control the emission direction. I didn't show here. We have a cavity, right? We have a cavity. I can control the visibility. I can control the smoothness of the face. And that kind of case, I can control the emission direction. This one is very important. When you track the war between Iran and Israel, you see there are many infrared weapons, or you can see the results, right? Because of high temperature. But using this kind of structure, we can locally control the direction of thermal photons For example, I can let the thermal photons emit along this way. So your camera here, you cannot see us. This one here I didn't show. This one can do that.
I understood. Is another one? Thank you. Só pegar um café. Congratulations. Okay. I have to go. We need to go.
Yeah. Thank you. Okay. Okay, so
we're going to move to the second talk of this seminar. And then we have the honor to introduce Dr. Zhang Gong. Dr. Zhang Gong is a young professor. So he was recently a national high-level young scientist program. Dr. Zhang finished his PhD in 2019 at Nanyang Technological University, Singapore. In his postdoctoral work at the Electrical University of Singapore, and did his postdoctoral work at the National University of Singapore. His work focuses on the photonic chip integration of quantum information technologies. He has published over 22 papers in top journals, including Nature Photonics, Science and Applications, Optical, and Quantum, etc. These are applied locally, internationally. He was awarded his young scholar work from Zhejiang University. He's a reviewer with top jobs, including applications, physical research, based on my box, Dr. Gong, without philosophy.
okay, thank you for the introduction and invitation for me to present here. So my name is Zhang Gong from Zhejiang University, also together with Dr. Hui. Today I'm going to introduce my work on using photonic chips for quantum information applications. So this presentation will be more like a basic introduction of what I do and why I do it. And I won't go too deep into the details. If you're interested, we can discuss offline. So first, yeah, Pruma has already introduced. We are Zhejiang University. Here's Shanghai. Here's Hangzhou. We are located basically in Hangzhou, and we have some offsite campuses. Each of the campus, they have their own buildings. So you're welcome to come to us for a visit. So for me, a little bit more about myself. Prof. You also introduced. So I was a PhD from Nanyang Technological University, Singapore, and postdoc in National University of Singapore. Now I'm an assistant professor in Zhejiang University. So my research can be categorized in two categories. One is the photonic quantum information, including like quantum number generator and quantum key distribution, and also the supporting components to support our research in quantum informations. So I'll go through some of the details. First, let me introduce slightly a background of what is quantum information. So quantum information utilizes quantum mechanics to achieve like applications in quantum communication or quantum computation. So for quantum communication, we basically use quantum entanglement or uncertainty principles to do secure communication or generate secure keys. So this here I show one of our achievements in China, which is the most quantum satellite. We can achieve across very long distance quantum key distribution. And also for quantum computation, it basically uses quantum superposition and interference to accelerate certain computational problem that is hard to do classically. So here I also show a quantum computer, something look like this. So it's quantum information is something that is guided by most major countries, China, US, EU, Russia. They all have their quantum research guidelines. So it's just the right time for us to do this kind of research. So one thing I want to solve is we need to use quantum to provide security. So why quantum security? There are basically two features, I would say. The first feature is what we call unbreakable security, also called future-proof. So basically, we use quantum phenomena to detect and avoid any potential eavesdroppers that may happen during our conversation. So we call it future-proof because we use quantum theories so that the sensitive data can remain secretive even after an unlimited time. So another feature is what we call self-validation. So this is required because somehow if we have a device that might be fabricated by a trusted source, or the device is trusted, but the performance is drifting during the operation. Maybe the device is in different temperature or in different working conditions. Maybe it's too old. The performance is not as good as before. So in this case, how do we know the equipment is working as we expected? It's providing quantum is as we expected. So that's why we need quantum to do self-validation. We have the user to validate during the operation to see whether the equipment is performing, operating at normal conditions. So basically, as a short summary, we can use quantum to provide a robust and transparent cryptography. It will decentralize the crypto with trust and return it to the user and service providers. The user can use quantum to verify the randomness or the robustness. And there are already some companies providing quantum products. The applications can be computational computing, cloud computing, and certifiable trust platform modules. And so for quantum security, there are basically two categories. One is the quantum random number generator, one is quantum key distribution. They are mostly the same in terms of the security proof and experimental setup. So I will just put them together. So for random numbers, the features we require from random numbers, the uniformity and also unpredictability. So based on the features, we might have different level of randomness. The simple one is pseudo randomness. Basically, when you use your program MATLAB or Python, press a random, it will generate some random numbers. Those kind of randomness from algorithms. So they can be easily broken if someone knows the random algorithm and also know the seeds. So that's why people are trying to explore the natural randomness from the environment. For example, there are people working on chaotic laser or the internal randomness from MOSFET, or even people can explore quantum randomness based on the internal randomness from quantum effects. For example, by measuring the sharp noise in a CMOS camera, or doing single photon entanglement measurement. So this kind of randomness is originated from quantum effects. So, as I mentioned, these randomness generation are required by the wearable device.
So if the device got hacked or the device is operating not as you expected, the randomness might not be as secure as before. So that's why we propose another new level of randomness is self-validation of the randomness. So we let the users to run some statistical tests to show the device is working properly. Another category is quantum key distribution. So as I explained, China has launched the quantum satellite. There are basically two types of QKD protocols. One is what we call a discrete variable QKD, where we encode the information in single photons. Then we use single photon detectors to detect the photon and retrieve informations. So for the discrete type, it typically has higher noise tolerance. It can achieve longer distance, but the speed will be slightly lower. And another type is what we call quantum continuum variable QKD. So it encodes the information in the quadrature of light, just like the coherent communication. And we use homoline detectors to detect the signal so that we can use simpler equipment and to achieve higher speed in short distance. So also we are trying to combine the advantage of from both the discrete variable QKD and continuum variable QKD to achieve like short distance, high speed, and experimental friendly. So here's a roadmap of QKD research. So starting from maybe 1990s, where people do tabletop proof of concept QKD experimental setup, then to this stage where fiber-based system emerge. People can use point-to-point with dark fiber to do QKD. And now we are roughly at this stage where commercialized products are available with higher speed and good longer stability. But what's next? So we think chip integration might be one of the potential directions. So why chip integration? Because we already have very mature semiconductor fabrication process and also materials we can use. And also for the small chip, we can have better phase stability, reliability, and also device density. We can integrate everything on very small chip. It's very high yield and high performance. And also, as I mentioned, there are already foundries can provide mass and low cost production. And also for the current photonic chips, we already have like laser ICs, active and passive components available. So it's just the right time for us to see how we can utilize it in quantum applications. So now the research directions can be something like we do chip integration, and we try to push the limit of the photonic chip to achieve higher speed. And also we do heterogeneous integration to integrate different functions and different materials with it. So yeah, that's what we thought of the roadmap. And then there are already some quantum photonic platforms. So starting from this work by Nanadu, the company building quantum computers in Canada. So they have silicon nitride chips for squeezing. They have lithium ion chip for switching, and also for using silicon for PDM modulators. And also there are people using silicon to utilize its high density functions to do large scale integration of quantum gates or CQKD. And also in one of the early work of the University of Bristol, UK, they use indium phosphide chips so that they can have lasers and modulators on the same chip. They also have silicon oxide nitride chips as very low cost, low loss delay line. And there are also people using laser written with guides. They can achieve low loss and high 3D integration, which is not possible from other platforms. And also, linear we can handle it. This is very good material for its Kaituno nonlinearity. It can be used to build modulators, squeezing, photon source. So as you can see, there are a lot of different platforms, and none of them are we are saying it's perfect. So that's why we think there are problems with chip quantum informations. For example, from protocol levels, typically the quantum information protocol will require, for example, high efficiency single photon detectors and low loss components, such as ideal components. And also for the chip, as I mentioned, no photonic chip platform currently is perfect for every applications. So that's why what we are doing is basically trying to develop better protocols plus better chips to achieve the optimum performance. So the first part I will explain is the quantum random number part. So why we do this kind of self-testing for the randomness. For self-testing randomness, the traditional way is to do device-independent way. So basically, why they call device independent, because it has basically no assumption on the device. As long as the input-output relationship satisfies some of our anticipation, we can know that the devices generate randomness from quantum effects. But this kind of device-independent framework requires super high efficiency single photon detector and very high efficiency integral photon source, and very hard to achieve experiment. So that's why there are works trying to improve the practicality with certain assumptions, practical assumptions, and which we call semi-device independent. So quantum system might look something like this. We will have a source, encode some quantum states, and then the receiver detected states. So from the three parts, we have different. We can have different assumptions to prove the practicality. For example, the source device independent protocol will assume that the source is not trusted, or the bounded energy and dimension protocol will assume that the emitting state has a limited dimension or limited energy, or the measurement device independent just assume the detector is not trusted. So why we think the measurement device is better is because the detector model is typically not ideal, and the characterization is much harder than characterizing some light. And also for the detector side, we have light input into the device, so it's harder to control. So that's why we want to make the detector side untrusted. And also, the previous work also demonstrated measurement device independent, but based on single photon detectors, and they are hard to integrate. So that's why we propose our protocol based on MDI QRG with homoline detectors. So the system looks like this. It contains the transmitter to prepare QEM states, and the receiver side is the homoline detector to measure the encoded states. And then, so for QEM states, they might look like this. It's QBSK modulation, or even we can do like higher level modulation, QEM16. So with this in place, as you can see from the figure, this is the quantum randomness expansion rate as the function of the homoline efficiency. So we are able to achieve positive randomness expansion at an efficiency of slightly more than 90%. And so, considering the high efficiency, we did a lot of work on homoline detectors to eliminate the electronic noise, and also we use super high efficiency PDs. In the end, we get somewhere around 91% efficiency, and we are able to do the experiment. So as you can see, the current requirement for the protocol is still quite high. So how do we implement a chip? So that's why we propose a slight modification to the protocols. We do a fine tuning on the output states so that we can get a better knowledge of what the states might look like by having more information from it. And with this protocol in place, we are able to achieve somewhere around 70% of homoline efficiency. Then this is when we can do it on chip. So for the chip integration, we try to use the standardized components from the photonic foundries. For these kind of devices, there are issues because the previous photonic foundries typically designed for classical communication. They target more on the speed rather than accuracy. For us, we really need to have an accurate encoded states. So that's why we spend some time to optimize, for example, the IQ modulators, design the control scheme to let us achieve pure phase modulations. So if you are familiar with silicon kind of modulators, you will know that the silicon modulator has phase loss dependency. So when we try to modulate phase, it will always come with a loss dependency with the phase. So in this way, we propose to use phase loss independent modulator. We drive the MVCN modulator in a push-push scenario so that we can find a proper working point where the intensity does not change, but the phase is perfectly 90 degree. And for IQ modulator, it's simple. We just drive with a very, very low voltage so that the distortion is minimal. And also for the homoline detectors, as you can see, at this stage, we are able to achieve somewhere around 100 megahertz bandwidth, but for noise clearance bandwidth, we are still able to use about 200 megahertz. And also the CMRR spectrum show that the CMRR is more than 65 dB, means it can suppress the classical noise very good. So as a result, the PD efficiency is somewhere around 76, and considering all the electronic noise and losses, the total efficiency we get is around 69%. And also, as you can see from this figure, we put a small triangle here, which is the simulation result. We assume that currently we have a higher efficiency PD in our hand, but not integrated in the system. By integrating the better PDs with the system, we anticipate somewhere around more than one order of magnitude higher secret key rate improvement. So yeah, another work related to random number generation is what we try to generate entanglement on silicon photonic chip. So what we try to generate is this kind of 0, 1, 1, 0 path entangled total states, and then we measure it using homoline detectors. So we try to design a loss equivalent scheme, so we can move all the losses in the detectors and also the electronic noise back into the transceiver side, so that we are able to get high speed and near ideal entanglement such as silicon photonic chip. So in this work, we improve the bandwidth of our line detector to somewhere around more than 10 gigahertz. And we perform a state tomography and CHSH validation to show that we are really generating the very good entanglement. So yeah, the results are shown here. And also another part of our work is the QKD common key distribution. So we are one of the first to demonstrate CVQKD on chip. So at the stage, we are using Gaussian modulated CVQKD protocol, and the bandwidth is somewhere around 3 megahertz and receiver efficiency 15%. But recently, we also upgrade the chip completely. We have achieved the discrete modulated CVQKD protocol together with polarization multiplexing, so that also we operate the whole chip with 20 gigahertz bandwidth and higher receiver efficiency of 33%. And as a result, the final secret key rate has going above 1 gigabits per second. So this is one of the results of CQKD. And also we try to develop new QKD protocols. We call DV-CVQKD. So the modulator side is DV-like encoding. We basically encode the states in time and phase. And then we measure it also using a homoline detector, but with a local oscillator. In this way, we don't really need to lock the phase of the local oscillator. We basically using the receiver side as a threshold homoline detector, and very similar to a single photon detector. So when the received signal is above a certain threshold, we assign 1. When it's below a certain threshold, we assign 0. In this way, we are able to detect the single photon states with a homoline detector. And with this scheme, we are able to achieve 15 kilometer fiber distance. So it's suitable for use as short distance with a very, very simple experiment setup. And then, yeah, as I mentioned, we build the 20 gigahertz CVQKD, which is basically based on this 20 gigahertz homoline detector. So at this stage, we are thinking The traditional transimpedance amplifier has limited bandwidth to somewhere around 1 maximum 5 gigahertz bandwidth. So how we can push the bandwidth further? We are thinking of whether we can use high bandwidth RF amplifiers. So in this way, we try to use the resistors as transimpedance to convert the photocurrent into voltage and then use RF amplifier to amplify the signal. So we perform a thorough analysis of this scheme and found out it's actually working. So at the very first stage, we are able to operate somewhere around 4 gigahertz 3 dB bandwidth. But as you can see, the shunt noise clearance can go up to 20 gigahertz. And in the paper I just mentioned, we further optimize some of the components, and we are able to achieve 3 dB bandwidth of 7.8 gigahertz with shunt noise limited bandwidth of about 20 gigahertz. And some of the other components, including the power limiter to protect QKD. So in QKD system, one of the severe attack or security loophole is what we call a Trojan horse attack. So when the QKD system is looking at this, Alex will prepare the state sending to Bob. We have a very strong assumption that both Alex and Bob's equipment are located in a secure place, cannot be touched by any eavesdropper. But what if eavesdropper can send a strong light through the fiber and collect a little bit of the reflected photons? Then it will get the information without disturbing the quantum states. So in this way, the information can be leaked to the eavesdropper without knowing by Alex and Bob. So that's why we need to do something to prevent this kind of attack. The typical method will include, for example, adding a photo detector in the transmitter to know that if there is some strong power shining in. But active components have problems because they can be easily bypassed. For example, if I shine very strong light, the detector might damage and cannot produce proper results. And that's why people prefer to use passive components, such as isolators, because passive components have limited degree of freedom. And isolators can allow the light coming in one direction, not the other direction. But the problem for isolators is it's really hard to integrate on chip. They are currently at least for our foundries, they are not able to provide this kind of materials. So that's why we are thinking whether we can use some simple material that can be easily get in our lab. So we try to use this kind of thermal optical defocusing effect to build a power limiter. Basically, is that when the light is strong, the prism itself will act as a contaminants. So the power that goes through the diaphragm and go through the output fiber will be limited. So as you can see from this figure, when we put the input power, the output power will always have a threshold. So we can use this threshold to know that there is limited amount of light coming into the device. And we also did a simulation in FDI computing systems to show that even if we have certain amount, like 10 to the power of -5 photons as Trojan horse photons, we are still able to get very decent transmission distance and secure key rate. And another very interesting component we developed is on-chip non-volatile switch, or let's say optical memory. We use ferroelectric chip material, hafnium oxide-based ferroelectric material, and cover directly on top of the silicon waveguide. And in this way, we are able to achieve non-volatile switching of the resonant peak of the array resonator. As you can see from this hysteresis loop, we will be able to see a very clear hysteresis loop indicating that the device has some non-volatile phenomena. And also we try to build single photon detectors. So we try to integrate it on silicon by both hybrid and heterogeneous way. So for hybrid way, it's quite simple. Just put one of the SPADs on the green couplers and see how much line we can get. The more elegant way is to try to do this kind of heterogeneous integration. We remove the substrate of the SPAD and directly couple to one of the waveguide. So we are able to achieve one of the highest efficiency performance for the market SPAs on the market. And we also developed some method to characterize the SPD, which we call the characterization toolbox, which is based on the decoy method, as I also mentioned before in the QKD system. So we are able to get a very rigorous bound for the noise SPD is contributed purely by single photon states. And this method comes with very rigorous proof and clear assumptions so that it can avoid any kind of non-ideal SPD model performance. And also we don't really require the prior knowledge of the detector on the test. Okay, that's basically me. So for the system level, we did research on QRMG and QKD. And for component level, we show that we built like power limiters, high bandwidth homoline detectors, and also the non-volatile memories. And consider future directions. Currently, since I joined Zhejiang University, we have a very strong background on photonic chip fabrication. We have like silicon, we have lithium ion interconnect, and also ferrite action material, and also phase change material. So we have quite a lot of different kind of materials. We are trying to bring different functions onto the photonic chip. Like we try to push for higher speed and better integration, and see if we can somehow use some of the things in practical applications. So this is our group. I'm working with Professor Dai Daoxing, who was the dean of our college. Most of the work I shown here is the work I was at done in Singapore, technology and the US. Thank you. That's all my presentation.
So, okay, hello, congratulations for the presentation. Very nice. I want to talk about the TIEs, when you do the CV for the information, and you have those, you show two things, right? One with the TIE, it's just a resistor, it's not external. And at least because normally it's slower typically if it has a active component, right?
Yeah.
But then you show one before that you have actually an active component there, the one that you showed before this one. And yes, so this guy.
To be honest, for the work I present here, we use our identifiers, or maybe for the low speed one. Yeah, this must be one we use a TI, but just commercialized TI.
It's not all integrated on chip. So
It's not integrated.
Because what I was about just that I saw the video that they integrated from Denmark, where they integrate the TI with one platform and then the photonic homoline detection another one, and they join it together, and they have really very high speed. Like for 20 gigahertz as well with 30 dB class. And but in your case, I think it's the other way around, right? Because we have the TIE integrated, you have like 3 megahertz of bandwidth, and you have fast response with just a resistor.
Yeah, it's true. So
Curious.
yeah, so for the TIAs at the stage, we don't really find quite a lot of commercialized products. And also for the paper you mentioned, I think if I'm not wrong, they also have one 3 bandwidth of very low, few gigahertz. So when we do this work, I don't think I showed here, but we did some research. They also do something like this. They say that they are able to operate at 20 gigahertz, but actually the 3 dB bandwidth is somewhere around less than 5 gigahertz.
Is the clearance. The 3 dB is the clearance. They're basically the same, like the same order of magnitude of your clearance.
Yes.
The clearance is close to 20 gig.
So yeah, that's why currently I'm also working on TIAs, and we are trying to get some different collaborators and vendors in China to see if we can push the limit of TIA, to see if we can get real bandwidth rather than just a shallow clearance.
In this case, just you do everything on foundry. or not apart, but some component with each other that can manufacture this for you?
For us, no. Yeah, the chip is from the foundry, the electronic chip is from another foundry, and then we do the packaging. Yeah,
Okay, thanks.
yeah, the full integration, I would say, is still quite hard.
No, just a question, regarding this, ferroelectric, application. Yeah, what is the speed of this, ferroelectric, phenomenon? Exactly, what is the speed?
Speed up. So at this stage, we only show somewhere around the actual microsecond switch time. So in our group, we anticipate that if we can properly dock the device, we are able to achieve like gigahertz level switch time. But in this work, we only demo somewhere around this. Actually, this material was from the electronics semiconductor field. They already used to build like ferroelectric components, memories and something. For this application, they are already showing like gigahertz level switching time. But for us, due to the limited docking ability at the stage, we only demonstrate something, I guess.
Okay, thank you. One question. Okay, well, thank you very much for your interesting talk. And, well, we are closing this seminar, but I'd like just to say that we have a very good relationship with this young university, and especially with the photonics groups from the university. And well, probably that we are going to get more closer in terms of collaboration. So if you are interested also in joining us in this kind of events, please let us know. And one of the goals is also to establish a WBE in different levels with the China University. Thank you very much for your attention, and just hope you join us in the next seminar. So we have a lot of seminars planned to be organized here. Okay, thank you very much.